You know that device you're holding? Or the one on your desk? There's this invisible engine inside it. And the crazy part is, it's always shrinking, but somehow getting way more powerful. So in this explainer, we're going to dig into how that incredible revolution happens, year after year.
I mean, think about it. We kind of just expect it now, right? You get a new phone and boom, it's faster. Your laptop gets thinner but runs games better than the old one. How does that actually work? How does it happen like clockwork every single year? Well, the answer is hiding in plain sight, except it's on a scale so tiny you literally can't see. Okay, so here's how we're going to break it down. First, we'll look at the big idea, this shrinking revolution. Then we'll dive into its golden age when everything was going great. After that, we'll see how it hit a massive physical wall. Then comes the cool part, how we got around that wall with a whole new dimension of thinking. And finally, we'll peek into the future, the next frontier. All right, so it all kicks off with this really simple but totally revolutionary idea. If you want to make your tech more powerful, you just have to do one thing: make its most basic, fundamental part smaller. That's it. And that tiny little part is called a CMOS transistor. I know, the name's a mouthful, complementary metal oxide semiconductor, but don't worry about that. Just picture a light switch, a ridiculously tiny light switch. Everything your phone or computer does, every single thing, is because of billions of these switches flicking on and off at insane speeds. They are, quite literally, the building blocks of our entire digital world. So for decades, the whole tech industry had this drumbeat they marched to. It was called Moore's Law. And what's interesting is, it's not a law of physics or anything. It was really just an observation that turned into a self-fulfilling prophecy. The idea was simple. Let's double the number of transistors we can fit on a chip every 2 years. And how do you do that? Well, you just keep making them smaller. And this, my friends, kicked off what we call the golden age of scaling. For a long, long time, progress was almost easy. It felt automatic. The roadmap was crystal clear. Just shrink the transistor and everything, and I mean everything, gets better. It was this beautiful, simple, powerful formula for success. The secret sauce behind this golden age, it was a principle called Dennard scaling. And honestly, it was like magic. It basically said that when you shrink a transistor, it not only gets faster, but its power use goes down too. So you get more speed and better battery life. You got all the good stuff with basically zero downsides. No overheating, no trade-offs. It was perfect. Yeah, it was the ultimate win-win-win situation. Think about it. A smaller transistor meant the little electrons inside had less distance to run, so it could switch on and off way faster. It also needed less juice to run, so it saved a ton of power. And, of course, because it was smaller, you could cram billions more of them onto the same tiny piece of silicon. This amazing cycle is what fueled the entire tech boom for decades. But you knew there was a but coming, right? That perfect, easy road, it couldn't last forever. As engineers got better and better at shrinking things, they pushed those transistors to be so small, they started bumping right up against the fundamental laws of physics. And that magic formula? Well, it started to fall apart. I mean, we are talking about the nanometer scale here, a world where you're measuring parts in atoms. Like a handful of atoms across. And when you get that small, the nice, predictable rules of electronics that we all learned, they start to get weird. Quantum physics takes over, and a whole bunch of new problems pop up that threaten to stop Moore's Law dead in its tracks. So 2 really big headaches showed up. The first one was something called leakage current. The best way to think about it is like a faucet that's supposed to be turned off, but it's constantly dripping. Electrons were literally tunneling through solid walls they weren't supposed to cross. Just poof, right through. This wasted power and generated a lot of heat. The second problem was short channel effects. Sticking with our faucet analogy, this is like the handle becoming too small and weak to actually shut off the water completely. The switch just wasn't reliable anymore. So yeah, the party was over. The easy path of just shrink it was done. To keep this whole thing going, to keep Moore's Law alive, engineers had to do something drastic. They couldn't just tweak the old design. They had to go back to the drawing board and completely reinvent the transistor from the ground up. And this is where things get really, really cool. This is where human ingenuity just blows you away. The problem was happening on a flat, 2D surface. So what was the solution? They had to think in 3D. They had to build up. You can really see this evolution in a few key steps. Okay, so we started with the original flat design, called planar. Simple enough. But to stop those leaks, Engineers literally pulled part of it up, creating a 3D fin. This was the FinFET. Now the gate could wrap around that fin on 3 sides, giving it way more control. And the latest and greatest, it's called Gate-All-Around, or GAA, and it's exactly what it sounds like. The gate completely surrounds the channel, like you're wrapping your whole hand around a tiny wire. This gives you maximum, absolute control. It basically plugs all the leaks.
But get this, just changing the shape wasn't enough. They had to reinvent the actual materials too. The old insulator, silicon dioxide, was acting like a leaky, crumbling wall, so they replaced it with something called high-K dielectrics. You can think of this as swapping out that old brick wall for a solid slab of reinforced concrete. At the same time, the old gate material got swapped out for new, advanced metals that could get a much better grip. It wasn't just a redesign, it was a total overhaul of the physics and the chemistry.
Okay, so that pretty much brings us up to today. We've solved these massive, once impossible problems with brilliant 3D designs and brand new materials. But you know how it goes. The race never stops. The push forward is relentless, and the next big set of challenges is already knocking on the door. Right now, the hunt is on for even crazier, more exotic materials. We're talking about things like graphene, carbon nanotubes, materials that are literally 1 atom thick. They're essentially 2D, but they have these mind-bending electrical properties. What everyone's looking for is the next silicon, the material that will define the next generation of computing. And all of this leads to a really interesting paradox in the modern world. On one hand, the cost to make a single individual transistor is basically zero. It keeps getting cheaper and cheaper while performance goes through the roof. But, and this is a huge but, the cost to build the factory that makes them has gone astronomical. We're talking tens of billions of dollars for a single plant. Why? Because when you're carving features that are just a few atoms wide, you need a level of precision and cleanliness that is, well, it's unlike anything else human beings have ever built. So that's the incredible story of the shrinking engine. It's a journey of just relentless, brilliant innovation, from a simple idea of make it smaller to completely reinventing things in 3D. But it leaves us staring at a massive question, doesn't it? We are now building switches that are literally a few atoms across. You can't really shrink that much more. So, what happens then? What does the next revolution in computing even look like when you finally run out of room to shrink?